Welcome to this comprehensive guide on finding the derivative of the cotangent function. Today, we'll explore one of the fundamental trigonometric derivatives in calculus, breaking down every step to ensure you understand both the process and the reasoning behind it. The cotangent function, written as cot of x, is defined as the ratio of cosine x to sine x. This can also be expressed as 1 over tangent x, since tangent is sine over cosine. Cotangent is one of the 6 fundamental trigonometric functions you encounter in calculus. The derivative of cotangent x is negative cosecant squared of x. Remember that cosecant is 1 over sine, so this result tells us how the cotangent function changes at any point. The negative sign is particularly important and often where students make mistakes. In this comprehensive tutorial, you'll master 2 different methods for deriving this result: the quotient rule and the chain rule. We'll work through detailed examples, highlight common pitfalls, and explore real applications in engineering and physics. By the end of this video, you'll have complete confidence in finding the derivative of cotangent and understanding why it works. Ready to dive in? Our first step will be to carefully define the cotangent function and set up our derivative calculation. Remember, understanding the why behind each step is just as important as knowing the how. Before we dive into deriving the derivative of cotangent, we need to establish exactly what the cotangent function is and what its derivative looks like. The cotangent function has 2 equivalent definitions. The first definition states that cotangent of x equals cosine of x divided by sine of x. The second definition shows that cotangent is the reciprocal of tangent. This means cotangent of x equals 1 divided by tangent of x. These 2 definitions are completely equivalent. We can use either one depending on which is more convenient for our calculations. Now, it's important to understand where the cotangent function is defined. Since cotangent involves sine in the denominator, we need to be careful about where sine equals 0. The cotangent function is undefined whenever sine of x equals 0. This happens at x equals 0, plus or minus pi, plus or minus 2 pi, and so on. In general, we can say that cotangent is undefined at x equals n pi, where n is any integer. Now that we understand what cotangent is, let's look at its derivative. This is the result we'll be proving in the next sections. The derivative of cotangent of x is negative cosecant squared of x. Notice the negative sign. This is crucial and a common source of errors. The negative sign is essential. Many students forget this negative sign, so remember, the derivative of cotangent is negative cosecant squared. Let's also recall what cosecant means, since it appears in our derivative formula. Remember that cosecant of x is 1 divided by sine of x. Therefore, cosecant squared of x is 1 divided by sine squared of x. This means we can also write the derivative of cotangent as negative 1 divided by sine squared of x. Both forms are correct and equivalent. In the following sections, we'll prove this derivative formula using 2 different methods, the quotient rule and the chain rule. Both approaches will lead us to the same result. Understanding these definitions and the final result will help you follow the derivations more easily. Remember, cotangent equals cosine over sine, and its derivative is negative cosecant squared. Now we'll derive the derivative of cotangent using our first method, the quotient rule. This approach treats cotangent as a fraction of 2 functions and applies the quotient rule systematically. First, let's recall the quotient rule. When we have a function that's the quotient of 2 other functions f over g, the derivative is g times f prime minus f times g prime, all divided by g squared. Now we express cotangent as a quotient. Cotangent of x equals cosine of x divided by sine of x. This fits perfectly into our quotient rule format. Let's identify our functions. We have f equals cosine of x and g equals sine of x. The derivative of f is negative sine of x and the derivative of g is cosine of x. Now we're ready to apply the quotient rule step by step. Let me clear the screen so we can focus on the derivation process. Step 1, we apply the quotient rule. The derivative of cotangent x equals sine x times negative sine x minus cosine x times cosine x, all divided by sine squared x. Step 2, let's simplify the numerator. Sine x times negative sine x gives us negative sine squared x, and cosine x times cosine x gives us cosine squared x. So our numerator becomes negative sine squared x minus cosine squared x. Step 3, we can factor out the negative sign from the numerator. This gives us negative times the quantity sine squared x plus cosine squared x, all divided by sine squared x. Now comes the key insight. We need to use a fundamental trigonometric identity to simplify this expression further. Here's where we use the Pythagorean identity. Sine squared x plus cosine squared x equals 1. This is one of the most fundamental identities in trigonometry. Step 4. We substitute the identity. Since sine squared x plus cosine squared x equals 1, our expression becomes negative 1 divided by sine squared x. Step 5. We recognize that 1 divided by sine is cosecant squared x. Therefore, our final answer is negative cosecant squared x. Perfect. Using the quotient rule, we've successfully shown that the derivative of cotangent x is negative cosecant squared x. This method demonstrates how the quotient rule can be systematically applied to trigonometric functions and how fundamental identities like the Pythagorean identity play a crucial role in simplification. This quotient rule approach gives us a solid foundation for understanding why the derivative has this particular form. The systematic application of the rule, combined with trigonometric identities, leads us directly to our result. Now we'll explore the second method for finding the derivative of cotangent using the chain rule. This approach offers a different perspective and demonstrates the power of rewriting functions in alternative forms. Step 1. We rewrite cotangent in a form that's suitable for the chain rule. Since cotangent equals 1 over tangent, we can express it as tangent to the negative first power. Step 2. We apply the chain rule formula for the derivative of u to the negative first power. The formula states that the derivative equals negative u to the negative second power times the derivative of u. In our case, u equals tangent of x, and the derivative of u equals secant squared of x. Step 3. We substitute our values into the chain rule formula. This gives us negative tangent of x to the negative second power times secant squared of x. Now we need to simplify this expression through several algebraic steps. Each step will bring us closer to our final answer. First, we rewrite the expression by moving the negative exponent to the denominator. Tangent to the negative second power becomes 1 over tangent squared. Next, we convert everything to sine and cosine. Secant squared becomes 1 over cosine squared, and tangent squared becomes sine squared over cosine squared. We can rewrite this complex fraction as a multiplication. Dividing by a fraction is the same as multiplying by its reciprocal. The cosine squared terms cancel out, leaving us with negative 1 over sine squared. Finally, we recognize that 1 over sine squared equals cosecant squared. Therefore, our result is negative cosecant squared of x. This confirms our result from the quotient rule method. Both approaches give us the same answer. The derivative of cotangent x is negative cosecant squared x. The chain rule method demonstrates the versatility of calculus techniques. By expressing cotangent as tangent to the negative first power, we transformed a quotient into a composition of functions, making the chain rule applicable. Now that we've learned how to find the derivative of cotangent, it's crucial to understand the most common mistakes students make and how to avoid them. These errors can lead to incorrect answers and confusion in more advanced problems. The most common mistake when finding the derivative of cotangent is forgetting the negative sign. Many students write the derivative as positive cosecant squared, but this is incorrect. The correct derivative of cotangent x is negative cosecant squared of x. Notice how the negative sign is crucial and must never be forgotten. This negative sign comes directly from our derivation using the quotient rule. When we simplified negative sine squared minus cosine squared, all divided by sine squared, we got negative 1 over sine squared. The second common mistake involves confusion with trigonometric identities. Students sometimes struggle to remember or correctly apply the fundamental relationships between trigonometric functions. Here are the 3 most important identities you need to remember. First, the Pythagorean identity. Sine squared x plus cosine squared x equals 1. Second, the reciprocal identity. Cosecant x equals 1 over sine x. This is crucial for understanding why our derivative involves cosecant squared. Third, the definition of cotangent. Cotangent x equals cosine x over sine x. This is the starting point for our quotient rule derivation. These identities work together in our derivation. The Pythagorean identity helps us simplify the numerator, while the reciprocal identity gives us the final cosecant squared form. The third common mistake is ignoring domain restrictions. Students often forget that cotangent is not defined everywhere on the real number line. Cotangent is undefined when sine of x equals 0. This happens at x equals 0, plus or minus pi, plus or minus 2 pi, and so on. In general, cotangent is undefined at x equals n pi, where n is any integer. This includes all multiples of pi. Consequently, the derivative negative cosecant squared of x is also undefined at these same points. You must always consider these restrictions when working with cotangent and its derivative. To help you remember and avoid these mistakes, here are some effective memory aids and prevention strategies. First memory aid: create a simple phrase like cotangent's derivative is negative cosecant squared. Repeat this phrase until it becomes automatic. Second memory aid: remember the pattern that all cofunctions, like cotangent, cosecant, and cosine, have negative derivatives. This pattern can help you remember the negative sign. For prevention, always double-check your work using this three-step process. Verify the negative sign, confirm your trigonometric identities, and check domain restrictions. Remember, the derivative of cotangent x is always negative cosecant squared of x. By being aware of these common mistakes and using these prevention strategies, you'll avoid errors and solve problems with confidence. Now that we understand the first derivative of cotangent, we can explore more advanced topics. Higher-order derivatives involve taking derivatives of derivatives, and they reveal deeper patterns in trigonometric functions. The second derivative of cotangent x is 2 cosecant squared x times cotangent x. This might look complex, but we can derive it step by step using what we already know. When dealing with composite functions, we apply the chain rule. The derivative of cotangent of u equals negative cosecant squared of u multiplied by the derivative of u with respect to x. Remember that integration and differentiation are inverse operations. Since the derivative of cotangent is negative cosecant squared, the integral of negative cosecant squared is cotangent plus a constant. For our first example, we'll derive the second derivative of cotangent x step by step. We start with what we know, the first derivative. Step 1. We start with the first derivative. The derivative of cotangent x equals negative cosecant squared x. Step 2. To find the second derivative, we take the derivative of the first derivative. This means we need to find the derivative of negative cosecant squared x. Step 3. We apply the chain rule to differentiate cosecant squared x. This gives us negative 2 times cosecant x times the derivative of cosecant x. Step 4. We know that the derivative of cosecant x is negative cosecant x cotangent x. We substitute this into our expression. Step 5. We simplify by multiplying. Negative 2 times negative 1 gives us positive 2. So our final answer is 2 cosecant squared x cotangent x. For our second example, we'll find the derivative of cotangent of 2x. This requires the chain rule since we have a composite function. We need to find the derivative of cotangent of 2x with respect to x. Step 1, we identify u as 2x, therefore du dx equals 2. Step 2, we apply the chain rule formula. The derivative of cotangent u equals negative cosecant squared u times du dx. Step 3, we substitute u equals 2x and du dx equals 2 into our formula. Therefore, the derivative of cotangent of 2x equals negative 2 cosecant squared of 2x. For our third example, we'll work with integration. We'll evaluate the integral of 3 times negative cosecant squared x. We need to evaluate the integral of 3 times negative cosecant squared x with respect to x. Step 1, we factor out the constant 3 from the integral. Step 2, we use the antiderivative relationship we learned. The integral of negative cosecant squared x equals cotangent x plus a constant. Step 3, we multiply by the constant 3 to get our final answer, 3 cotangent x plus c. These advanced considerations build upon our fundamental understanding of the cotangent derivative. The second derivative involves products of trigonometric functions. The chain rule extends our ability to handle composite functions, and the integration relationship connects differentiation with antiderivatives. Higher-order derivatives become increasingly complex, but follow the same systematic approach. We've covered a lot of ground in this comprehensive exploration of the derivative of cotangent. The most important result to remember is that the derivative of cotangent x equals negative cosecant squared x. We learned two powerful methods for deriving this result. First, the quotient rule approach, where we treated cotangent as cosine over sine and applied the quotient rule formula. Second, the chain rule method, where we rewrote cotangent as the inverse of tangent and used the chain rule. There are several key points you should always remember. The negative sign is absolutely crucial and is the most common source of errors. The result involves cosecant squared, not cosine or sine. Both derivation methods give exactly the same result, which confirms our work. And always watch out for domain restrictions where sine equals 0. This derivative has wide-ranging applications across many fields. You'll encounter it in engineering calculations, physics problems involving oscillations and waves, signal processing applications, and throughout advanced calculus courses. Understanding the derivative of cotangent is essential for success in calculus and its applications. The techniques we've learned here will serve you well in more advanced mathematical topics. Thank you for watching this detailed exploration. If you found this helpful, please give it a like and subscribe for more mathematics tutorials. Feel free to leave questions or suggest future topics in the comments below.